Hello everyone, this video is brought to you by the Atılım University OpenCourseware project for the course Physics 101. The lecture notes are prepared by Associate Professor Dr. Hüseyin Oymak and the video lectures are prepared by Ümit Alkuş. In this video, we will solve one problem in Chapter 10. A disc of radius small r, which is 11 centimeters, and mass capital M, which is 2.5 kilograms, is initially at rest. A rope of negligible mass is wrapped around the disc at one end, and at the other hand is a block of mass small m, 1.7 kilograms. Now, the disc is set to rotate freely. A. Draw the free body diagrams of the system. B. Find the acceleration of block M. C. Find the tensional force on the rope. D. Find the torque exerted by the rope on the disc. E. Find the angular acceleration of the disc. And F. Find the angular speed at the cylinder at t equals 5 seconds. The rotational inertia of the disc is I equals 1/2 times capital M times r squared. First, we write the given quantities in SI units. In part A, we draw the free body diagrams for each object. Since the disc is rotating, we cannot represent it by a point. We draw it as it is. Here, the only force acting on this disc is nothing but the tensional force on the rope, and it is a downward force. Because there is a rotation, we draw the angular acceleration as this. And the free body diagram for small m is drawn like this. Here, A is the linear acceleration of mass m. Okay, that's all for the free body diagrams of the system. In part B, to find the acceleration of block M, we utilize the Newton's second law, which is F net equals m times a. Here, F net in the direction of a equals m times g minus t. And we find an expression for linear acceleration as m times g minus t over m. To find an expression for tension, we make use of the definition of torque, which is tau equals r cross F. Here, force F equals to tensional force on the rope. Since the angle between the tensional force and r is equal to 90 degrees, we have tau equals r times t times sine 90 degrees, that is r times t. Then the expression for tension T is obtained as T equals tau over r. In this formula, we can use the formula for tau as tau equals I times alpha. And the expression for linear acceleration is alpha times r, and alpha equals a over r. Then we put these values into tau and then into t to get t equals I times a over r squared. The rotational inertia of the disc is given as 1/2 times capital M times r squared. Then we obtain the tension as capital M times a over 2. If you put this expression into the equation of motion for small m, we obtain m times g minus capital M times a over 2 equals m times a. Therefore, we obtain an expression for a. Now, we put the corresponding numerical values into this formula to get 5.6475 meters per second squared. which is approximately 5.65 meters per second squared. In part C, we find the tensional force on the rope by this formula. T equals capital M times A over 2. Substituting the corresponding numerical values into this equation, we obtain T as 7.0593 newtons, or approximately 7.06 newtons. To find the torque exerted by the rope on the disc, we use this formula for the torque that we have found in part B, that is tau equals capital T times R. We insert the numerical values into the corresponding places, and we obtain the torque as 0.77652 Newton times meters, or approximately 0.777 Newton meters. In part E, we use this formula to find the angular acceleration, that is alpha equals A over R. We put the numerical values into this equation and finally get 51.340 radians per second squared, or approximately 51.3 radians per second squared. In part F, to find the angular speed of the cylinder at t equals 5 seconds, we use this formula. Now, we substitute the numerical values into this equation, and finally, we obtain the angular speed of the cylinder at t equals 5 seconds as 257 radians per second. Okay, this is the end of the discussion of this problem. Thank you for your attention and see you in the next video.